Welcome to Unit 2. We'll be studying polynomial functions. Our learning goals will be to determine the behavior of graphs. Let's take time to do a little review. Hit pause and figure out which one is the graph of 3x to the third power. Hopefully you pick C. Hit pause on your second review question and analyze f of x equals 3x to the third power and see which one of these choices you will make. Hopefully you picked D. And now we're going to talk about, in our last units, we definitely analyzed graphs, and this time we're going to graph polynomial functions and we're going to determine the real zeros and turning points. Here is some of the vocabulary you will hear throughout the lesson. We're going to start off by graphing transformations of monomial functions. Let's take a look at this problem right here. F of x is equal to this expression raised to the fifth power. What do we know about this problem? Well, we know that it is an odd degree function. How do we know that? Here we see the degree is to the fifth power. So this is going to be similar to our parent function, y is equal to x to the third power. So this graph is going to be shifted, take a look here, it's going to be shifted 3 units to the right. When I say this graph is going to remind us of our parent function, y equals x to the third power, maybe you can remember from your previous algebra class that on the left-hand side, the arrow is down, and on the right-hand side, the arrow is up. This works for all odd degree polynomials. So here's our sketch of the graph. Take a look. On the left-hand side, the arrow is down, and on the right-hand side of the function, it is up, and it has that similar shape of our cubic function. And let's not forget to mention, it is definitely shifted 3 units to the right. Let's take a look at this monomial function. First thing we want to ask ourselves is it an even degree or odd degree? So you want to look at your highest power. Your highest power is a 6. That's an even number. This is going to be an even degree. So this one is going to follow the graph of our parent function y equals x squared, which is also an even degree. What we want to do is we want to look to see what is our transformation here. So we have -1, so we know it's going to go down 1. So we have an idea of what this graph is going to look like. So let's graph it. So here we have it. We have our even degree. We see that on the left-hand side, the arrow is up, and on the right-hand side, the arrow is up. All even degree functions with the leading positive coefficient, leading coefficient that's positive, both arrows are going to be up. So let's go ahead and take a look at this graph. F of x is equal to 2 plus x to the third power. Which one do you think it is? Hopefully you picked B. When you take a look at it, we see that our degree is a 3. It is an odd power. We expect our graph to be up on the right and down on the left, and we expect a vertical shift of +2. So here we have the rules for the leading term test. So if your degree is odd and it's positive, we are going to have one side on the left down and on the right side going up. If the degree is odd and the leading coefficient is negative, on the left-hand side, it's going to be up. And on the right-hand side of the polynomial, it's going to be down. Now let's take a look at our even powers. If it is an even degree and it's positive, we expect on the left, the arrow will be up, and on the right, the arrow will be up. If it is an even degree and it's negative, we expect on the left for it to be down and on the right for it to be down. This will be an easy way for us to be able to write our end behavior without even graphing the function. So go ahead and read through this problem and see how you would determine the end behavior. So here we go. So there's two things I want to look at. I want to look at the degree. So I'm looking at each one of the exponents, and I see my highest exponent is 4. So the degree here is a 4th degree. I want to look at my leading coefficient, and my leading coefficient is positive. So if it's an even degree with a leading coefficient that's positive, I know that the ends are going to be in the air. That's going to help me to write my limits. And here we go. Take time, pause here, and see what you come up with. Okay, so here we go. What I want to do first is I want to look at the terms. I want to find out what my degree is. The degree is going to be the highest exponent. Oh, here it is. It's a 5. So this is going to be a 5th degree polynomial. So this is a 5th degree. And the coefficient, when we put it in standard form, is going to be, the leading coefficient is going to be positive. Because I know it's odd and it's positive, it's going to be down on the left and up on the right. That is going to help me write my limit of the end behavior. And voila, here we go. Here's a multiple choice question for you. Describe the end behavior of the function using limits. Explain your reasoning using the leading term test. Hit pause. All right, hopefully you picked C. Now let's talk about zeros and turning points. So when we talk about zeros, we want to look at the degree of the polynomial. So for this example right here, 3x to the 6th power minus 10x to the 4th minus 15x squared. The degree is going to be a 6th degree. So if it's a 6th degree polynomial, at most, and we want to use the word at most because it will be no more than, at most 6 real zeros. Okay, that means it could cross the x-axis in 6 distinct places. To find out what the turning points are, what you want to do is you want to subtract 1 from the degree. So because this is a 6th degree, we should expect to have at most 5 turns. Can we have less? Yes. Can we have more? No. Okay. So as we take a look at the graph here, I want to see how many real zeros I have. I have 1 here, 1 here, and 1 here. So it's crossing or touching the x-axis in 3 places, in which we said it has to be at most 6, so we're good there. And let me use another color. Let me use yellow to show the turns. So here's where it turns here, and it turns right here, and it turns right here. If you look, those are your places, your extrema. But we like to think of it as if you're driving. So this is me, and I'm driving, and I have to make a turn because I'm going in a different direction now. And I get up here and I make a turn, and I'm going into a different direction and I make a turn. So this one particular graph has 3. At most, it can have 5. So we're going to read this next question. We're going to state the number of possible real zeros, turning points, and then we're going to actually determine the real zero. So let's start off by stating the possible real zeros. So the possible real zeros, we're going to find that by looking at the degree. So the degree here is 3, so it's a 3rd degree. 3rd degree. And so possible at most 3 real zeros. How many turns? At most 2 turns. So let's just make sure we're answering the question. State the number of possible real zeros. We did that. And the turns, we've done that. And now it says determine all the real zeros by factoring. So let's get started and let's factor this. So what we want to do is, the first thing, we want to let our f of x be equal to 0. So this is going to be 0 is equal to x to the 3rd power plus 5x squared plus 4x. So I have it in standard form. I want to see if there's a GCF I can take out, and it is. So when I take out the GCF, I have x times x squared plus 5x plus 4. Now I can factor this right here into x plus 4, and x plus 1. We're going to use the zero product property, which means we're going to set every factor equal to 0. So we will get our first factor will be x is equal to 0. The next one will be x plus 4 equals 0. And this one will be x plus 1 equals 0. This is going to help us determine what our real zeros are. So here we have a real 0 at 0. We have a real 0 at x equals negative 4, and we have a real 0 at x equals negative 1. Well, take a look. Here are zeros that we found. Here they are graphed on this graph, and this is definitely consistent with a cubic function, having at most 3 distinct real zeros. And check out the terms. Here's 1 and here's 2. These type of rules will help us to graph without even needing a calculator. So I want you to hit pause here. I want you to state the number of possible real zeros, the turning points, and then I want you to determine all the real zeros by factoring. Well, hopefully you picked A, and if you struggle with that, stay tuned for the next slide. So if you struggle with that last problem because it was x to the 4th power, we're going to talk about how to take those quartic problems and solve them as if they were a quadratic. We're going to put it in quadratic form. So take a look here at x to the 4th minus 5x squared minus 14. We're going to take that expression, we're going to rewrite it. We're going to let u equal x squared. So check it out when we rewrite it. This will now be x squared minus 5x minus 14. So this will be an easier way for us to be able to factor quartic. So let's get started. So keep in mind, we still have to follow the directions, and it does say state the number of possible real zeros and the turning point. So let's just go ahead and do that first. The possible real numbers are going to be 4 because our degree is 4, and the turning points are going to be 3. So I'm going to put that right there. We already know that. We're going to determine all the real zeros by factoring. So we start off and we have 0 is equal to x to the 4th minus 4x squared plus 3. We're going to go ahead and write this in another form, quadratic form. And we're going to rewrite it as u squared minus 4u plus 3. So now we're ready to factor, and we're going to put it into factor form. U and u, we need the product that's going to come out to 3. So that's going to be 3 and 1, and we need them both to be negative because the negative 3 times a negative 1 will give us that positive 3. We're going to set each factor equal to 0. Let's see what we get. Actually, before we set each factor equal to 0, we're going to go back to plugging in what u was equal to, and that was equal to x squared. Because remember, from the beginning, we let x squared equal to u so that we could substitute and still factor this. Now we're going to set each factor equal to 0. So this will be x squared minus 3 is equal to 0. And this will be x squared minus 1 is equal to 0. This here will give us x is equal to plus or minus the square root of 3, because I moved the 3, add 3 to both sides, and then take the square root. Over here, the same thing. If I move the 1 to the other side, add 1 to both sides, and take the square root, and get x is equal to plus or minus 1. Let's see where we go from here. Here we go. Here's our graph, and here are the 4 distinct real zeros. We got plus the square root of 3, minus the square root of 3, minus 1, and plus 1. They're all on this graph. And remember, we said at most it could have 3 turning points, and here we got 1, 2, 3. All right, so as we wrap up our lesson, I would like for you to state the number of possible real zeros and the turning points, and then determine all the real zeros by factoring. Go ahead and hit pause, figure out what your answer is, and you'll type that in at the end. Thank you.